zu klappen. Start recording. Works. Ich glaube, was er sagt hier.
Kannst du mal ganz normal mal drin haben, eine normale Lautstärke.
Die Sonne tönt nach alter Weise im Brudesphären Wettgesang und ihre vorgeschriebene Reise vollendet sie mit Donnergang. Ihr Anblick gibt den Engeln Stärke, da keine dich ergründen mag. Die unbegreiflich hohen Werke sind herrlich wie am ersten Tag.
Ist okay so, oder?
Ja, passt ja zur kosmischen Strukturbildung.
Gut, lassen wir es mal so.
Wir können jetzt eigentlich so weitermachen. Das ist mal ein anderes Programm.
Was nochmal schieben?
So, good afternoon, everybody. Let's start. A nice program for today. First, I wanted to introduce the notion of a correlation function of a power spectrum. Second, I wanted to show you that the eigenvalues of the Seldovich deformation tensor have a very peculiar probability distribution, which phenomenologically and intuitively explains already what the large-scale arrangement of cosmic structures should look like. That's the program for today. But what did we do last time? Remember? Spoke about trajectories. We introduced Seldovich trajectories as reference trajectories and showed that the force acting relative to them obeys the potential of that force, obeys a Poisson equation that is only sourced by the nonlinear density. Very important. Then we talked about random fields, in particular Gaussian random fields, and I showed you the central limit theorem that explains that if you suppose independent random numbers drawn from the same distribution with finite mean and variance, you invariably get a Gaussian field. All right. So far, so good. Before we start, do we have any questions on what happened last time? Not the case. Anybody following the lecture notes as they are growing? And watering them are growing? We should look at them. Pick the fruits. All right. So, correlations. We need correlations. Suppose we have a random field psi. Could be anything, and could be the density contrast, could be the wind speed in the atmosphere, could be the height above sea level on the Earth, random field. So that depends on some spatial position Q1. I multiply this with the same random field at a different spatial position, and I take the average. This is called the correlation function. And it will generally depend on both positions Q1 and Q2. So that's the correlation function. Statisticians usually divide by the variance of both fields and get the correlation coefficient. And it's normalized to lying between 0 and 1, but usually we use this expression here without the normalization as correlation. All right. If the correlation function depends only on the difference of the coordinates, not on both of them separately, this is called a homogeneous random process. And it's translation variant. And of course, since we are dealing with cosmological fields, we will always assume that our random fields will have a homogeneous correlation function. And also, if in addition, the correlation function depends only on the modulus of the difference between the two positions, then it's also isotropic. Same remark as before. Since we are dealing with cosmology, the general assumption that the universe is spatially homogeneous and isotropic, we will typically assume that correlation functions are also homogeneous and isotropic. And then we can write the correlation function simply as a function of one scalar quantity, namely the distance between the 2 points, irrespective of where it points, where the separation vector points, and irrespective where what the point is from which we calculate the correlation. Okay. Now suppose we take Fourier transforms of this Gaussian random field. As we saw not yesterday, last time, the Fourier transform of a Gaussian is a Gaussian. Therefore, if you Fourier transform a random field, you get if you Fourier transform a Gaussian random field, you get a Gaussian random field. So suppose we take Fourier transform psi, and we perform the same operation now with a Fourier transform. So what is this? It's going to be the average of an integral over Q1 with the notation that I introduced last time, and the integral with the subscript Q1 of psi of Q1 e to the minus I K1 times Q1. That's one Fourier transform. The other one is this. Integral over Q2 psi of Q2 e to the minus K2 average closed. Now the average acts only on the random field, of course. Right? So I can pull the averaging brackets under the integrals, pull the integrals out front. So I have integral over Q1, integral over Q2. Now, if I take the average of psi of Q1 times psi of Q2, I get the correlation function of psi as defined above. I'm assuming homogeneity and isotropy. So I just get psi of Q1 minus Q2 absolute by assumption. Right? This doesn't follow unless I make these assumptions. Then e to the minus I K1 times Q1. Okay. And now I write Q2 in a different manner. Then we write e to the minus I K2 times Q1 minus R. So I write Q2 equals Q1 minus R. The difference vector between the two. All right. Now you see, instead of the coordinates Q1 and Q2, I can introduce the coordinates Q1 and Q1 minus Q2. The correlation function depends only on the difference. And then, if I integrate over Q1, I get a delta function here, a delta distribution in K1 plus K2.
So excited, I don't know. I know something. It's marvelous.
Do you need any help?
No.
Any water? A wet sponge? I would throw it to you. All right. So we get this delta distribution here of K1 plus K2. Look, this is a consequence of the random field being homogeneous. This is why this delta function appears. It's very important that it appears. Now the rest is an integral. Now over the coordinate r only, right? The difference vector. And this is now psi of r e to the minus I, no, plus I K2 times vector r. Okay. But this delta function tells me that K2 is minus K1, and otherwise I just get 0. So I replace this by minus K1, so that I get the Fourier transform of the correlation function here. And this is called the power spectrum. P psi of K1. And of course it's isotropic as well. Right? So it can only depend on the absolute value of the wave vector or the wave number K1. Now, of course, the K1 is superfluous, right? I can just call it K. Therefore, let me write me write this in the very shorthand notation here. Average value of the Fourier transformed Gaussian random field, 2 pi cubed delta distribution. Now let me write it. Psi tilde times psi tilde prime. That's psi tilde evaluated at k1 prime. You get the delta function between the two, and I get the power spectrum of k here. That's the power spectrum Fourier transform of the correlation function. As you see, they are related by a Fourier transform, so they are equivalent. Sometimes it's easier to deal with the correlation function. Sometimes it's easier to deal with a power spectrum. This is a very important quantity, which tells you that Fourier modes, the Gaussian random field, are independent of each other, right? Because this gives you a non-zero result, or this average here gives you a non-zero result only when the wave vectors are equal and opposite, equal in size, opposite in direction. All other Fourier modes are independent of each other. Okay, that's what I wanted to say about correlation functions and power spectra. Now, because of the isotropy of the correlation function, you can calculate these, you can proceed a little further with these Fourier transforms. Let me just write this down because you often see the corresponding expressions. So if you want to Fourier transform this psi of r, e to the minus I k times r, integrated over r, we can orient the coordinate system such that the k vector points along the polar axis. Then we have rotational symmetry about this polar axis. Then we can introduce the polar angle between the two, between k and r. R is varying over the entire sphere, but the k is remaining fixed. So this is going to be an integral over d phi, that's the rotation angle about the z-axis, from 0 to 2 pi, but nothing in the integral depends on that. Then we have an integral over d mu. Mu is the usual direction cosine for the angle between the k-axis and the r-axis. So this is an integral from -1 to +1 in d mu. That's the integral over sine theta d theta from 0 to pi. And then we have an integral over r squared dr from 0 to infinity over psi of r e to the minus I k r mu. You can integrate over phi, gives you a factor of 2 pi. You can integrate over mu. That's easy with the exponential here. This gives you a 2 times sine kr divided by kr. Sine kr, because you have to evaluate this exponential at plus and minus 1. Division by kr, because of course if you integrate this exponential, you get a factor of 1 over kr. So this is 2 pi integral r squared dr, 0 to infinity, psi of r, sine kr divided by kr. That's one way of writing this, and the other way of writing this is that this is the 0th order, first kind, spherical Bessel function, J0. Often you see this, and you know where it's coming from. It assumes isotropy, and then you can proceed in that way. Of course, now, once you have a power spectrum, you can go and Fourier back transform it. The only thing that changes is that then you have a plus sign here. This doesn't affect the Bessel function. You get the same expression for the power spectrum. If you have the if you just exchange now power spectrum and correlation function, you get exactly the same result. All right. So far, so good. Are there questions about these things? All right. I'm going to proceed to what I said earlier and to have a closer look at the probability distribution for the eigenvalues of the Seldovich tensor. This is going to be really cute. But it's going to take a while. I need to ask for your patience. Promising, right? It's going to be nice. The whole result that I'm going to show has been calculated or has been shown for the first time by Doroshkevich right after Seldovich came up with the Seldovich approximation. So that's an old result. But I think it's totally underrated. I think it's a very important result. And since Doroshkevich's derivation is essentially unreadable, not only because it is in Russian, it's worth going through it again. Trying to raise the suspension level. Does it work? So, remember, Seldovich, very good. Seldovich said the position of a particle at time t, position means co-moving position, time means growth factor, right? Is given by its initial position plus t times initial momentum. And we saw that this is, in fact, a very good approximation because deviations from the Seldovich approximation are given by a gravitational force, which is sourced only by the nonlinear density contrast. All right, so this is already very good. Looks so simple, but nonetheless, it's very good. All right, and then we saw that we can assume that the initial velocities or momenta, doesn't matter, are drawn from a Gaussian random field such that the momenta are the gradient of a scalar field, the velocity potential. Why Gaussian? Because of the central limit theorem. Why the gradient only? Because rotational modes decay. You saw this on problem sheet number 2. I'm sure that everybody of you looked into it. All right. So this means that the Jacobian of the Seldovich trajectory, right? So the derivative of the final position with respect to the initial position. This is given by the unit matrix plus t times the Hessian of psi. Now I'm looking into the properties of the Hessian of psi. Okay, the d2 psi is the matrix of second derivatives of psi with respect to the initial coordinates, q initial. So that's a 3 by 3 matrix. It's symmetric by Schwarz theorem. Because it is symmetric, I can orthogonally diagonalize it. It will have 3 eigenvalues. And then we are going to look at the probability distribution of these eigenvalues. All right, so let's start saying that I compose a data vector for a Gaussian distribution consisting first of the 3 diagonal elements of this tensor, psi11, psi22, psi33, by which I mean the second derivatives of psi with respect to q1, q1, q2, 3, 3. And then, of course, we have the mixed derivatives. So I'm ordering all the components of this, all the independent components of this 3 by 3 tensor in form of a vector. And now I'm looking at the covariance matrix of this vector. In other words, I want to look at psi11 times psi11 average, psi11 times psi12 average, and so on and so forth. Right? I want to correlate every one of these vector elements with every other. So I want to do things like that with arbitrary indices I, j, k, l being taken from 1, 2, 3. What is this? I'm going to write this in terms of the Fourier transform because I want to relate all of these averages to the power spectrum. Power spectrum of psi, first of all, but we'll see about that. All right. So what is this? If I write psi as integral over its Fourier transform, in this way, then you see that each derivative with respect to any of the coordinates is going to return a factor of I, k with an index corresponding to this. Right? Now I want to cross-correlate these derivatives of psi at the same point. Right? So I'm looking at one particular point in space. I'm correlating psi ij with psi kl at this point. So this means that the Fourier phase is going to be 0, because the difference vector between the two positions that I'm looking at is going to be 0. And so the Fourier phase is dropping out. It's just a factor of 1. So these things look as follows. Right? There's a minus sign. There's a minus sign because I get 2 factors of I down due to the derivative. But this is going to happen for these 2 derivatives. For these 2 derivatives. Nice. No factors of I, no minus sign. All right, then if I take this Fourier transform, the Fourier transform of this field here as a function of k prime, and this Fourier transform here as a function of k, the delta function, which comes from the homogeneity of our random field, will ensure that k prime is minus k. But I'm taking a double derivative. So no minus sign from that either. And the only thing that happens is that I need to integrate over k, now over ki, kj, kk, kl. Fourier transform of psi times Fourier transform of psi, that's going to be a power spectrum of psi of the complete wave number k, no phase factor, right? Because I'm correlating the 2 expressions at the same time. Okay, this is an integral over the complete k space, which means that if any one of these k components here is lonely, unpaired, the integral is going to be 0. This is independent of direction. If, for example, I would have here k1 times any other k, and the k1 would be alone, then the integral would return 0. So this means that this result is positive only if any of these four indices are pairwise equal. Okay? If there was a lonely index remaining, the result would be 0. If there was an odd number of equal indices, same thing. So either I or j must be equal, then k and l have to be equal, or I and k, or I and l, and so on and so forth. So I only have to consider very few of these cases here. Let's consider the first case of two equal indices. Then, by isotropy, I can pick which index I want to take. And because it's easiest, I'm looking at psi 3,3 times psi 3,3. This is representative for all of them, right? Psi 1,1, psi 1,1, psi 2,2, psi 2,2, psi 3,3, psi 3,3 must be the same. I'm looking at only one of them. All right. So then I have k3, 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 k3. So that's an integral over k to the power of 4 times mu to the power of 4. Mu is the directional cosine as before, right? Times c psi of k. I can carry out the phi integral. I can, of course, carry out the mu integral. There is no phase factor anymore, right? That's easy to do. So what is left over is just a factor of 2 pi. I'm leaving some space in here, which I have to correct. We'll see about that. Then the integral over mu is just giving me 2/5, right? It's giving me mu to the power of 5. I need to evaluate this at the boundaries -1 and +1. This gives me 1 over 5 plus 2 plus 1 over 5 gives me 2 over 5. And finally, I have an integral k to the 4 p psi of k. But then remember, this integral with a subscript k is an integral over d3k divided by 2 pi in brackets cube. I must not forget this factor. And since we have the d3k here, I need to multiply with k squared dk. And then the integral goes from 0 to infinity. Okay? So what have I done? I have used isotropy here to say that indices must appear pairwise. I have used isotropy once more to say that such quantities where the same pair of indices appears in both factors must all be the same irrespective of the index. I took the simplest, K3. Gives you this result here. Now, this is 1 over 5, 1 over 2 pi square integral k to the 4 times p psi. You looked at the problem sheet, didn't you? So we know that Laplace square psi is minus the initial density contrast. If I go with this to Fourier space, the equation reads minus k squared psi tilde equals minus delta Fourier transform. So this means that k to the 4 times the power spectrum of psi equals the power spectrum of delta. So this is just k squared dk p delta of k from 0 to infinity. And for reasons that will become clear much later, we call this sigma 2 squared. That's just a moment of the power spectrum. It's an integral over the complete power spectrum. It's going to be a number. It's a number that characterizes the amplitude of the density fluctuation power spectrum. We call this sigma 2 because of this exponent 2 here. So this is just sigma 2 squared divided by 5. All right, now all the other elements here are components where one index appears pairwise and the other pair of indices is another number. The simplest case is going to be psi11 times psi33. And that's going to be all we have to calculate. Right? So this is going to be k to the 4, 1 minus mu squared times cosine square phi times mu squared times p psi of k. Why is this so? Look, now I have k3 squared. This gives me a k squared times mu squared. Then I have a k1 squared, which is k squared times sine square theta. This gives me the 1 minus mu squared. And then I have another factor of cosine square phi from the x component of the k vector. That's all. Now what is this? Let's carry out the phi integration first. It's going to give you pi. Why? Because sine square phi plus cosine square phi is 1. And the integrals over sine square phi over the complete circle equals the integral over cosine square phi. So the integral over cosine square phi needs to be 1/2 of that. What do you get if you integrate 1 from 0 to 2 pi? So it's pi. And the phi integration is gone. Now, here we have a mu square integrated. That gives you a factor of 2/3. Then you have a mu to the 4 integrated. That gives you 2/5. And we have done the theta integration. And all that remains is the same as above. Right? So this is 1 over 2 pi cubed times the integral 0 to infinity k to the 4 p psi of k squared dk. I tend to mess up these numbers now. So let's see. I'm taking a 2 out here, right? Then I have 1/3 minus 1/5. So this 5/15 minus 3/15. This gives you 2 over 15. So this here is 2 over 15. Okay, now sorry for the mess I'm creating here, but this is going to be 1 over 15 times 1 over 2 pi squared, right? I want to have the same prefactor as above, times the integral 0 to infinity k squared dk p delta of k. So this is again sigma 2 square. So this is sigma 2 squared divided by 15 and not divided by 5. So it's 1/3 of what we got if all indices were equal. And of course, it's not a surprise that it is 1/3 because we have 3. So now, okay, and of course, all the others are 0. Right? So the whole covariance matrix shrinks to the following expression. So sigma 2 squared over 15, and now we have a 6 by 6 matrix. And of course, I'm not writing a 6 by 6 matrix now. in fact like this, right? There's a 3 by 3 matrix M to be specified. It's the unit matrix here, and there are zeros everywhere else. And M is 3, 3, 3, 1, 1, 1, 1, 1, 1, right? Which reflects that we have either 3/15 or 1/5 or 1/15 on the off-diagonal element. So that's our covariance matrix. Are you with me? It's not so difficult, eh? Yeah.
So basically, what we need not only what thing when we say something like the integrals that we write down are really well defined, making some sort of assumption, even if we don't know what the shape of this homogeneous function is, maybe it's Gaussian or something, that it's basically something that's very well resolved, right? So that correlations are not well resolved then in turn in real space. That's fair to say.
Well, we have only assumed that we can Fourier transform the Gaussian random field. That we can Fourier transform psi. Yeah, I mean, true, we assume that sigma 2 squared exists. That's true. Otherwise, we only assume that we can Fourier transform the Gaussian random field.
We want something like this to be true, and our function needs to satisfy if it's a Gaussian or maybe another homogeneous isotropic field or generated by one needs to be nice.
Well, its power spectrum needs to be nice. Right? Psi itself is only characterized by its power spectrum because it's assumed to be a Gaussian random field. The power spectrum needs to be nice enough such that sigma 2 square exists.
And is it then fair to say that nice enough means that the correlations are not strong on the distance with the
No, it isn't. I mean, d delta of k can extend to k equals infinity. It needs to die off faster than k to the minus 3 at large k. That's the only constraint we have. It needs to be faster than k to the minus 3. Yeah, yeah. Satisfied? All right. That's the covariance matrix. Now we need two things. We need its determinant and we need its inverse. And this is really easy. The inverse you can just read off. This is this. Try if you don't believe. Straightforward, right? If you have a block matrix like that, the determinant is also very easy. Let me write it like this. It's going to be sigma 2 squared divided by 15 to the power of 6, of course, right? Because we have a 6 by 6 matrix. And now we have determinant of m times the determinant of 1. Determinant of m, believe it or not, is 20. Determinant of 1 is left for you to calculate. It's 20, obviously, right? It's 3 times 8 minus 1 times 2 plus 1 times minus 2, So it's 24 minus 4. All right. M to the minus 1. Try it yourself, right? This Cramer's rule, for example, if you want to construct it. Otherwise, just multiply the 2 and see that's correct. Good. So we have our inverse. We have the determinant. Isn't this lovely? Now, of course, we know what the probability distribution for our complete vector D is. This is something we don't want to know. But nonetheless, we know what it is. So this is 1 over 2 pi to the power of 6, determinant of C. So that's 20 times sigma 2 squared to the power of 6. So that's sigma squared to the power of 12. If sigma 2 is getting that, right? 12 is a fairly high power. Nonetheless, square root of 15 to the power of 6. So that's 15 to the power of 3. That's our normalizing prefactor. And then we have exponential of minus a half. The complete data vector D, psi 1, 1, psi 2, 2, psi 3, 3, psi 1, 2, psi 1, 3, psi 2, 3, okay, times the inverse of the covariance matrix times D. All right, but we are aiming at a probability distribution for the eigenvalues only. We are not aiming at a probability distribution for all of these tensor elements. So what do? We wipe the board. Now I want to use that I can diagonalize the Seldovich tensor, or the Hessian of the velocity potential. And I know from the spectral theorem that there is an orthogonal transformation that diagonalizes it. So I know that there exists an orthogonal transformation R such that the Hessian of psi that I've been looking at is given by RT times a diagonal matrix that I call lambda times R. Okay? I know that an R like that exists. And lambda is shorthand for the diagonal matrix containing only the eigenvalues of the Seldovich tensor. All right. Now I need the Jacobian of this transformation. Right? This transformation will turn my original data vector D into lambda 1, lambda 2, lambda 3, 0, 0, 0. I need the Jacobian of this transformation. The degrees of freedom of these orthogonal transforms are the 3 Euler angles. So I want to know how I can express the integration over all of the tensor elements, all of the elements of the Hessian of psi, into an integral over d lambda 1, d lambda 2, d lambda 3, and then something else that contains only the Euler angle. How do I do this? I need a metric for the space of these matrices. All right. I start with a scalar product for matrices. Suppose you have a square matrix, you have square matrices A and B, then you can define a scalar product of A and B like trace of A times B. Okay. Then I'm going to use that the line element in the space of such matrices is given by the scalar product of the differential of any square matrix S. You see, I know that I have a square matrix here. I need to know the line element in the space of these matrices here. I'm using the scalar product here in order to write a line element like this for the trace of ds squared. So S is shorthand for the d squared psi here. So now I'm taking the differential of this expression here. This is going to be dr transpose times lambda times r plus r transpose d lambda times r plus r transpose lambda times dr. Okay? We know what d lambda is. D lambda 1, d lambda 2, d lambda 3. I don't know yet what these drs is, but now, if you recall theory 1, right, the section on the Euler angles, R transpose times R is the unit matrix. So this is 0. So the dr transpose times R plus R transpose times dr equals 0. And since this is the transpose of that, this matrix here, dr transpose times R, is an antisymmetric matrix. It's going to be important later on, but should be known. So in other words, I can rewrite this as dr transpose times R transpose times lambda times R, right? I'm switching a unit matrix in between here. I'm leaving the center term as it was, and I'm writing here R transpose lambda R times R transpose times. What am I doing? I'm doing this. And I'm also switching a unit matrix in between here. All right. Now I use that dr transpose times R is minus R transpose times dr. Times RT lambda R plus R transpose times d lambda times R. And here I'm using that R transpose times dr is minus dr transpose times R. So minus R transpose lambda R transpose, no, dr transpose times R. Okay? So now you see all these terms begin with R transpose and end with R. So I can pull one R transpose to the left, and I can pull one R to the right, which is a very good thing in view of the trace that we have to take. So this is R transpose times something big, d lambda, minus dr times R transpose times lambda, minus lambda R dr transpose times R. Okay. We are unfortunately not done yet. There is one crucial step in this calculation that I need to explain. Okay, so let's return to this one here. Now I start with this equation once more, but now I say at the same time R times R transpose to see the unit matrix. So dr R transpose is also 0. So this is going to be dr times R transpose plus R times dr transpose. So I'm using this in order to write this term here by its negative with the factors exchanged like this. So this means that the differential of our Hessian matrix, this is given by R transpose d lambda plus R times dr transpose times lambda minus lambda times R dr transpose. That's the commutator of these two matrices. Okay? Times R. Okay, now taking the square is really easy. So I have to square this. I have to take the trace. If I square that, and R will meet an R transpose here in the middle, they will shake hands and disappear. Then an R transpose followed by a lot, followed by an R, can be cyclically exchanged under the trace. They meet, they disappear. So what is left over is just that ds square, right? Our line element in the space of 3 by 3 matrices, of diagonalized 3 by 3 matrices. This is given by the trace of d lambda square plus the commutator squared, and the mixed terms are all gone. Why is that? Because if you pull the commutator apart and you take into account that the matrix R times dr transpose is antisymmetric, and that lambda is of course symmetric, you see that the mixed terms fall victim of a contraction of an antisymmetric matrix with a symmetric matrix, and therefore the mixed terms go away. Next thing is also recalling theory 1. Right? Since R times dRt is an antisymmetric matrix, is characterized only by 3 numbers. Right? Diagonal elements have to be 0 anyway. Off-diagonal elements mirrored on the diagonal have to be negative. So only 3 of the elements of R times dr transpose can be independent, and they are usually set in the following way. That you define the 3 components of vector of an angular velocity, and you can write this matrix like that. The whole calculation tells you some tedious but easy steps. That's the result. All right, now this will be an infinitesimal rotation here. So all these omegas will be infinitesimal elements of this angular velocity vector. And it's going to be an angular velocity vector in the Euler angles. But what you see here is that now in a differential geometric language, this line element here represents a Euclidean metric with respect to the following differential: d lambda 1, d lambda 2, d lambda 3, that gives you this. Then plus, not sure about this factor 2 here really. For the sake of the argument, let me just remove this, because it doesn't really matter. Now we have absolute value of lambda 1 minus lambda 2, omega 3, plus absolute value of lambda 1 minus lambda 3, omega 2. Sorry, no, these are differentials here. So if you want to speak in differential geometric language, these are the dual bases here with respect to which this line element becomes Euclidean. If you want to think of the omegas here as being differential in the Euler angles, just think of omega 3, omega 2, omega 1 as differential quantities. The most important thing is that these differences of eigenvalues appear here. And they do so because, first of all, here we have a commutator and here we have an antisymmetric matrix in the omega. Okay? So, but this means now that we can integrate over all the Euler angles. I'm going to show you how. So we started from a Gaussian distribution for all the tensor elements. Let me write this down again. We said that P of D is some normalizing prefactor, whatever that is, right? 15 to the power of 3 divided by the square root of 2 pi to the power of 6 times sigma 2 squared to the power of 12. And a factor of 20 and so on and so forth. A number. Exponential of minus 1/2 times d transposed times c to the minus 1 times d. That was where we started out from. And now we said we are going to transform the data vector d by the diagonalization of the Hessian of psi, or the Seldovich tensor, to lambda 1, lambda 2, lambda 3, 0, 0, 0. That was the result of our diagonalization, right? This was the whole point. Now, by this result here, we know what the volume element is that we have to integrate over. Right? So P of d times dd, this is going to be n times the exponential of minus a half. Let me just write q for the quadratic form, d transpose times c to the minus 1 times d, times d lambda 1, d lambda 2, d lambda 3, now times these differentials here. Lambda 1 minus lambda 2, lambda 1 minus lambda 3, lambda 2 minus lambda 3, and I have to take the absolute value and take this of all three factors together. And then I have the differentials omega 1, omega 2, omega 3, into which in some way, whatever, the Euler angles will enter. But now, you see, because we have transformed the whole data vector to lambda 1, lambda 2, lambda 3, 0, 0, 0, the quadratic form in here does not contain the Euler angles anymore. Okay? They're gone. Because the covariance matrix looked like this. What did it look like? The Euler angles also don't couple to anybody else. So this means that I can integrate out all the Euler angles. And if I integrate over all the Euler angles over their definition ranges, that just gives me a factor of 2 pi squared. Okay? And of course, the quadratic form will be independent of any rotation, right? Because it's a quadratic form. So I can evaluate the quadratic form once and for all in the frame in which the Seldovich tensor is diagonal. So in other words, I can write 2 pi squared. That's the result of integrating over all the Euler angles. 2 pi squared number. But now you see, if this data vector only has the first three elements populated, of course, evaluating the quadratic form is going to be very simple. It's just the vector lambda 1, lambda 2, lambda 3 transpose times the matrix m to the minus 1, the 3 by 3 matrix, times lambda 1, lambda 2, lambda 3. This is now the complete quadratic form. And now we have lambda 1 minus lambda 2, lambda 1 minus lambda 3, lambda 2 minus lambda 3. D lambda 1, d lambda 2, d lambda 3. And all the dependence on the Euler angles is gone, and we have a probability distribution for the eigenvalues only. All right, if you wish, you can, of course, now evaluate with the inverse of m this quadratic form. Now let me write the complete thing. So this is 2 pi squared times the number times lambda 1 minus lambda 2, lambda 1 minus lambda 3, lambda 2 minus lambda 3, absolute exponential of minus a half. Aha. Now you see, if you insert the matrix M as I gave it to you about before, right? Remember, m to the minus 1 was 4, 4, 4, minus 1, minus 1, minus 1, minus 1, minus 1. divided by a factor of 10. Of course, and I need to take into account that the prefactor of the covariance matrix is 15 divided by sigma 2 squared. So I need to multiply this also by there. So this was the matrix m to the minus 1 as I gave it to you before. Now we have to multiply by 15 divided by sigma 2 squared. Then we get a factor of 15 over 10. That's a factor of 3 over 2. So we get, you never won, do you? What the hell? Yes. So we get this common factor for all of them. And now we have 4 times lambda 1 squared plus lambda 2 squared plus lambda 3 squared. And then we get all the negatives twice, right? Once from the upper diagonal and from the upper triangle and once from the lower triangle. So we get minus 2 times lambda 1, lambda 2 plus lambda 1, lambda 3 plus lambda 2, lambda 3. Now, of course, if you feel like doing that, you can cancel a factor of 2 and so on and so forth. That's not important. This is the main result, and it's an extremely important result. I do not expect at all that you memorize these steps. The main point is just, once you know the statistics of the underlying Gaussian random field, you know the statistics of the components of the Seldovich tensor. Once you do that, you use that you can diagonalize it by any, no, not by any, by a specific orthogonal transform. From the diagonal form of the Seldovich tensor, you can get to any representation of the Seldovich tensor by any choice of the Euler angles. So we integrate the Euler angles out, and we saw that this does 2 things. First of all, we get this product of differences here. Second, the subsequent integration of the Euler angles just gives you a factor of 2 pi squared. But this is the most important step. And if you trace this back, you see this comes about because all these rotations, or the differentials of all these rotations, are antisymmetric matrices. That's the reason why these differences appear. Now, what does this tell us? What does this tell you? Well, first of all, we get this beautiful derivative, no, not derivative, this beautiful remains of a Gaussian here. Okay, it's just an exponential function. But this prefactor here is most important because it tells you that the probability for any of these eigenvalues to agree is 0. Okay? Now, what would it mean if the eigenvalues agreed? Suppose all the 3 eigenvalues agreed. Then you could write this Jacobian here as t times lambda, the only eigenvalue that is still remaining, times the unit matrix. So this would mean that you would have an isotropic contraction or an isotropic expansion. But this is not possible. The eigenvalues cannot agree. So this means isotropic expansion or shrinking of a cosmic volume starting from a Gaussian random field is impossible. Spherical collapse is forbidden. This is the most important question, most important result. It's not even allowed that any 2 of them are equal. Cylindrical collapse is also forbidden. So what is allowed? What is allowed is that one of them is largest, and then the other 2 have to be different. We will have collapse along the along the eigendirection that belongs to the largest eigenvalue first. So any cosmological volume that you pick will shrink or expand along one direction first and will transform into a sheet-like thing. Then there will be a next eigenvalue, next in size. This will belong to an orthogonal eigendirection, and that will shrink next. So the first thing that you will form are sheet-like structures. The second thing you will form are filamentary structures. So the messages of the whole long calculation, if you want, forget about the calculation, but I think it's mathematical tricky, so it's also nice to see. Nonetheless, the most important message is spherical collapse is forbidden. Even though gravity is, of course, isotropic, spherical collapse is forbidden from a Gaussian random field. Second, what you will form is a sequence of sheets and filaments. Because not even any two eigenvalues can be equal, so cylindrical collapse is also forbidden. All right? And this is why, very quickly after the Seldovich approximation came up, Seldovich started to talk about the formation of pancakes. He used the Russian word for that, blini. Nonetheless, right? This is the origin of the term pancakes in cosmology, right? This probability distribution here. Okay, so spherical collapse is forbidden. Cylindrical collapse is forbidden. Anisotropic collapse is allowed. This leads to the formation of the cosmic network. And if you ever saw a picture of cosmological simulations, what did you see? You saw a cut through a network of filaments and sheets. This is the reason. And as you see, this is inevitable for any dynamics beginning with a Gaussian random field, right? Because we started analyzing the eigenvalues of the Hessian of the velocity potential. No more, no less. What you do with that is a matter of dynamics. Here we have very simple dynamics, right? Just multiplied by time. Could be different dynamics as well. The point is, not any two of these three eigenvalues can be equal. So this means that the formation of sheet-like or filamentary, in any case, anisotropic structures is a very natural thing starting from a Gaussian random field. And what you saw from the central limit theorem is that a Gaussian random field itself is a very natural thing. So this means that the formation of sheet-like or filamentary, in any case of network-like structures, is a very, very universal thing to happen in nature. From a Gaussian random field, the deformation is going to be anisotropic. All right. Now suppose you sit by the side of a swimming pool. It's about the right time of the year. The sun is shining, of course, right? Like today. And you look at the caustics that the sunlight makes on the bottom of the swimming pool. If you have a wave pattern on the surface of the swimming pool, there are people swimming in that, they create a wave pattern, all of them. Of course, they are uncorrelated, right? Usually, the swimmers, not always, but most of the time they're uncorrelated. So you have a random superposition of a random field. The wave pattern on the surface of the swimming pool is going to be Gaussian no matter what. The sunlight shining through the surface of the pool and finally arriving on the bottom of the pool is going to be mapped by Snell's law, right? Very easy dynamics as well. But again, you have the deformation of an incoming wave pattern by a Gaussian random field. And what do you see on the bottom of the swimming pool? A pattern of sheets and filaments. So this means that the pattern of sheets and filaments that you see in the swimming pool has exactly the same reason as the pattern of sheets and filaments that you see in the cosmos. For exactly the same two reasons. The central limit theorem and the probability distribution of the eigenvalues of this Hessian matrix. Okay? You needed to see this. Absolutely. And now we can move on. Do you have any questions? Are you satisfied? All right. As I said, right, the original result goes back to Doroshkevich. I think it's a paper of 1.5 pages or so. Yes. I don't know. Your point is completely correct. You know, you look at this result, you see, okay, I realize spherical collapse is impossible. Let's continue with the spherical collapse model. This is what you do in cosmic structure formation if you do it the conventional way. And then what happens is that you get results that seem to resemble observations very well. And that's the only justification. I don't know why this works. I really don't know why this works. I mean, it's completely awkward. Right? 1972, Gunn and Gott came up with the spherical collapse model. They were pretty innocent because I'm pretty sure that they did not know the Doroshkevich result. They introduced the spherical collapse model, and yeah, okay, then press Flechter built their theory upon that, and it seems to work. And then you find out, wait a moment. We are dealing with spherical collapse that must not happen. You get results that work very well. I have no idea why. Or let's say I have only suspicions why. Suspicion is that you're making statistical statements, and the orientation of these principal axes of the Sadovich lens that change all over the place. So on average, on a very large average, the structures become spherically symmetric. And I think that's the reason, that may be the reason why this works. But you're completely correct. Right? You begin most conventional treatments of cosmic structure formation with stating the existence of somebody that is not, of something that is not there. So strictly speaking, you're dealing with the empty set, but okay. You looked like you had a question. Oh. Okay. Let's come to kinetic field theory. All right, so what starts now is our specialty. And this is something we have developed here in Heidelberg. And it's very much things in progress. So what I'm showing you now, or what I'm entering into now, is a snapshot of what we think is right now. I told you before that we wanted to have a description of a cosmic density field or a cosmic velocity field or whatever that avoids by construction the shell crossing problem. Remember what the shell crossing problem was? If you start, for example, with the hydrodynamical equations and you build cosmic structure formation theory on top of them, then you have the problem that as soon as matter streams cross, and they can't cross in a fluid, but they can cross in reality, then you would have to deal with a multiply valued velocity field at individual points in space, and hydrodynamics is not able to deal with that. This is the origin of the shell crossing problem. And we wanted to have a description that avoids that. I told you before that if you look at particle trajectories in phase space, you know beforehand that they cannot cross because solutions to the Hamiltonian equations are unique once you fix a point in phase space that you start the trajectories from. All right. So I'm imagining a slice through phase space on which I fix initial conditions. This would be, for example, very early in time. And from this point, I launch a trajectory through phase space. It's going to lead somewhere. But one thing is for sure, it's not going to meet another one. So if I start here, this one also does its thing, but they are certainly not going to cross. Lovely. They follow what we call the Hamiltonian flow. Right? All of these trajectories are controlled by the Hamiltonian equations. So if you think of a bundle of trajectories here, this is what we call the Hamiltonian flow of phase space, or of a section of phase space. All right. And now I color these points here in a different way, by which I mean I'm assigning different probabilities to them. And I'm assigning occupation probabilities to these points in the initial slice of phase space here. And I know that these colors are going to be transported along these trajectories. And they may mix in a completely psychedelic way, but in such a way that I can in a differentiable way map the final state to the initial state and vice versa. All right. This is essentially all that kinetic field theory does. We are covering the initial slice of phase space with a probability distribution. And this probability distribution tells you with what probability a point xi on the initial slice in phase space is going to be occupied. Then we multiply this with a transition probability for a point moving from the initial point in phase space to a final point x in phase space. Now I can integrate over all initial phase space positions, and I will get the probability for the final point x in phase space to be occupied. This is a very similar thing to what you do in quantum field theory, for example. In quantum field theory, this transition probability here is a difficult thing. Since we have to do with classical particles, this transition probability is very, very simple. Because you know that from any initial point in phase space, there's only one possible, there's only one possible point in phase space that I can read. I can say that this whole transition probability here is a delta distribution, which I can write in the following way. It's a delta distribution that tells me only if the points x and xi in phase space are related by a solution of the Hamiltonian equation, the transition probability will be non-zero, and otherwise it's going to be zero. And of course I need a delta distribution here because an integral over that needs to be unity. Now there's a specialty about this because the argument of this delta distribution is a function. Right? So this is what we call a functional delta distribution. All right. This is the main thing. Now, remember thermodynamics. The central piece of thermodynamics is a partition sum. What is a partition sum? It's a sum over probability distribution times an exponential. This exponential can contain different things. It can contain a chemical potential or whatever. Now we are constructing a partition sum for this complete set of particles. There's one crucial difference, though, between the partition sum in thermodynamics and the partition sum that I'm going to write down now. In thermodynamics, you deal with equilibrium properties of systems. And you imagine that you bring systems in contact or bring them out of contact, and you wait until equilibrium, thermal equilibrium, mechanical equilibrium, phase equilibrium, whatever this may be, as established. It will take an amount of time that depends on the strength of the interactions between the particles, but ultimately you imagine that equilibrium sets in, and then thermodynamics describes the equilibrium state. We can't do this here, right? Because first of all, there is no equilibrium in a self-gravitating system. This is something that the virial theorem tells you already. And second, the expansion of the universe drives the quantities that are going to appear now in our partition sum, right, will be functions of time. So we will have an equivalent of a partition sum, but an equivalent that does not just contain numbers like the chemical potential or the temperature or anything like that you know from equilibrium thermodynamics, but it's going to be a functional functions of time. So we replace the generating functional by we replace the partition sum by a generating functional. How do we do that? We take the probability with which a certain state is occupied at a certain time in phase space, and we multiply this with an exponential factor very much like you would introduce a chemical potential, for example, in the grand canonical description of thermodynamics, where you would have an exponential of mu times n. This appears here. The factor of I is convention. That's purely conventional. You could leave this out as well. And this quantity J here is a quantity that is related to the trajectories x in the same way as, for example, the chemical potential is related to the particle number, a grand canonical thermodynamical description. The only purpose of introducing the J here is that later we can bring factors of x down by taking functional derivatives with respect to J. So exactly in the same way as a derivative of a thermodynamical grand canonical partition sum with respect to the chemical potential gives you the mean particle number, the derivative of this expression here, our generating functional, with respect to the field J, gives you an average position. We're going to use that later. Now, x are the trajectories as functions of time. So x are functions. So we need to integrate over functions here. So this is a path integral. property of this being a path integral will very quickly get lost again. But let me write with a curly capital D here, just to emphasize that we are integrating over all possible trajectories. Therefore, we are integrating over functions. Therefore, this is a path integral. And this is our generating functional as a function of the source field J that we have introduced here. All right. Now we can put all of that together and say Z of J equals an integral over all paths, an integral over all initial positions. This is an ordinary integral. This is a path integral. P of xi, delta d of x minus x bar. Let me just write it in this way, right? You know what this means. This is the transition probability now times e to the power of j in x. I need to tell you later what these parentheses mean and so on, just to illustrate that. Now, of all these paths here, this functional delta distribution picks out exactly one, right? Which is the solution of the Hamiltonian equations beginning at xi. So this is just an integral of the initial probability distribution with which the positions in phase space are being filled, times e to the power of I j times x bar. And we know what x bar is, right? We talked about particle trajectories already. dxi. So let me write the fundamental result right here. Z of j equals integral over some initial phase space measure, d gamma, times e to the power of I j x bar. This is our generating function. And now we need to deal with that, right? But this contains essentially the entire theory. D gamma is P of xi dxi. And you see I'm using notation in which all the particle positions or trajectories or so are compressed in one symbol. And of course, we need to be much more accurate about this next time. But this is the idea, right? You plant a bundle of trajectories on the initial phase space with a certain probability assigned to each of these trajectories. You transport them forward with the Hamiltonian flow. In this way, you create this generating functional, and later you read off the generating functional whatever you want to know. Correlation functions. Okay? Next time. Thank you for your attention. Don't forget, spherical collapse is forbidden. Not much, because I have a committee meeting at 5 and I need to go home before.